Today we are going to start Electrostatic Potential, Chapter 2. So this is very interesting and simple to learn, provided if you have thorough with the first chapter topics. Now, what do you mean by electrostatic potential? So before we move into that, we know that gravitational force and spring force we have learnt in 11th classes. So all these two forces we have proved that it is conservative force. Conservative force means 4 definitions you can say, but here what I meant was that is total energy is conserved. In what way? Okay, let me start the gravitational potential energy only. So gravitational force, when you keep a ball over here, this ball will be acted upon by a force, that is gravitational pull will be there. The gravitational force will be equal to what? mg. So what is the force acting on the ball when you place it over the point A? That time it will experience a gravitational pull that is equal to what? mg in the form of weight. So the force due to the gravitation is nothing but what? It is equal to mg. Now, due to the Earth's acceleration, okay, due to the gravity. Next, if you want to move the ball to a height h, this to the point B through a height h, then what you are supposed to do? You have to do some work. For doing the work, you need to apply the external force. One force is pulling it downward. So in which direction you need to apply the force? In the upward direction, because you want to move the ball in the upward direction. So you need to apply the external force in a direction opposite to this gravitational force. So minimum force required is what? Minimum force required will be equal to what? Minimum force that is applied externally will be equal to the gravitational force that is equal to mg. But in which direction it is applied? It is applied in the negative direction. So can I write F external is equal to minus Fg? Because the gravitational pull is downward. You are moving it upward. So the external force should be applied upward. That means this force is downward. You are trying to move it through upward. So the external force is upward. And in which direction the object is moving? The upward direction. The displacement is happening in this way. So what is work done? The work done by the external force. What is the formula? Do you remember? It is Fs cos theta. Here what is the theta? The theta both acting along the same line. So the theta will be equal to 0. So it is nothing but Fs. So what is the work done in moving the ball from A to B? This is nothing but external force, right? So WAB will be equal to F into S. What is F external? Here you are applying the external force and you are moving through your distances. So can I write F external into S? What is the displacement that it is happening? It is nothing but H. So you are moving through the head. So F external into H. What is F external? Applied force is nothing but minus Fg into H. What is Fg? The force due to gravity is nothing but mgh. So this is nothing but this minus sign simply represents the external force. It's applied in a direction equal to the gravity. So what is the work done? Work done is a scalar quantity. Work done is simply nothing but what? mgh. So scalar quantity. So the negative sign indicates you can write. The negative sign is nothing but what? Work done. That is external force is equal and opposite to the internal. That is gravitational force. Magnitudes are equal and F external is opposite to the gravitational force. So this work done stored as what? The work done in moving the ball from A to B is stored as potential energy. The external work done will be stored as potential energy. And you have written the potential energy at a height h is mg. Okay, what I can write? Suppose if you consider the potential energy at the ball of the ball at A is UA. Potential energy is represented by the letter U. And the potential energy at the point B is UB. So what I can say, the amount of work done is nothing but, since it is a conservative force, amount of work done is nothing but what? The change in the potential energy, that is final minus initial. So work done in bringing a charge from, bringing a ball from the point A to the point B, moving a ball from A to B is nothing but what? change in the potential energy. Okay, so simply what the work done will be stored as potential energy in the ball. As soon as you release the ball, on releasing the ball, what it will do, ma'am? The ball gains kinetic energy. Ball gains kinetic energy and it starts coming down. Right? And at any point, if you calculate the kinetic energy and potential energy, they will remain constant. That is the sum of the kinetic energy and potential energy will remain constant. That is nothing but the total energy. The total energy of the system remains constant. So that's why we call this as conservative force. The same thing you can apply here in Coulomb's law. Coulomb's force is a conservative force. While teaching Coulomb's law, I told you already and I explained what is conservative force there in detail. So, the Coulomb's force is conservative force. So, the same concept we can apply in Coulomb's forces, charges also. What it is? So, here the energy we call it as electrostatic potential energy. Why we are learning here? That is important, right? Without knowing that without knowing the title, how will you learn the chapter? So this is the electrostatic. Here whatever we are talking about, here it is mass energy, that is gravitational potential energy we see. But whatever we are talking about with the Coulomb's force, we call it as electrostatic potential energy. Now, what is that? So in order to learn that, let us consider a positive charge Q. It is the source charge and this source charge produces electric field. It is stationary, fixed, and at any point you can consider it is the source charge, not source energy. It is the source charge and it produces electric field. The electric field can extend up to, it is spherically symmetric, you know, I am considering only one line. So this electric field will extend till infinity. If you keep a charge at infinity, it will not experience any force. But when the charge is at the point A, now consider the charge is, you are bringing a charge plus Q naught at the point A. So when the positive charge Q naught is kept at the point A, it will experience a repulsive force due to the positive charge Q. This big charge will repel this small charge Q naught. Here the consideration is important. The Q naught is considered in such a way it will not disturb the configuration of capital Q. What do you mean by configuration? Big term? No, ma'am. It is very simple term. It will not deviate from, that is disturbed from its position. It is sitting there aram se, right? Then it will not be disturbed because of this Q naught. Why? The Coulomb force is equal and opposite, right? See, when two bodies A and B are, when Q1 and Q2 are kept at a distance R, then force on 1 due to 2, force on 2 due to 1. They are equal and opposite, right? So if I talk about positive charge Q, this will repel this small Q naught. But at the same time, if I keep a significant charge at this point, this will also start repelling, right? This one. That I don't want. Okay. So that's why the consideration is like that. This Q naught will not disturb the configuration. If it disturbs, this Q naught will keep on moving. Then we cannot calculate anything. Okay. So that's why this configuration will not be disturbed. Now, when I keep the positive charge at Q naught, it will experience electrostatic force of repulsion that is given by Fe and it is acting in this direction. Now, I want to apply something and I want to bring this charge from A to the point B. I don't want this charge to be at A. I just want the charge to move from A to B. But there is a villain. That is electrostatic force will not allow me. Then what I should do? I should apply external force. That external force, how should I apply this? External force must be equal and opposite to the electrostatic force. Minimum force, how much you need to apply? I am not talking about maximum. Minimum force, how much you need to apply? Be applied will be equal. That we know. And it should be opposite, right? In which way you want to move? You want to move this way. So the external force should be applied in a direction opposite to the internal force. But not internal force, the electrostatic force. So F external will be equal to Fe and the negative sign indicates what? It is in a direction opposite to the electrostatic force. Okay, in which direction you want to move? You want to move in this direction. The displacement is happening from A to B. Right? So the direction is also in this direction. So what is the small work done? by the external force, small work done or work done by the external force. Here you just take work done by the external force. When we do the derivation, that time you consider small. Work done by the external force is nothing but what? Work done in bringing or in moving the charge Q0 from A to B will be equal to what? This force and the displacement, correct? How much you are making that? This is external force, and this force, external force, is nothing but what? It is nothing but the electrostatic force into the total displacement. This is the work done by the external force, and this external force, it is done on the charge. So the work done on the charge will be stored as electrostatic potential energy. Is it clear? Simply, you need to remember whether it is gravitational energy or electrostatic energy or spring energy, work done will be equal to nothing but what? Change in potential energy. Again, I will go to this side. Work done is nothing but potential energy. Why I have written change in potential energy? It is also very simple. From where to where we are moving, A to B we are moving. So, at this point A, if the potential energy is UA, and at this point B, if the potential energy is UB, then how much you need to do the work? The amount of work done is nothing but what? The change in the potential energy. Can I write like that? You start with a zero amount of, that is zero money, and you do some work and you are earning 100 rupees. That means, how will you relate your work done in terms of money? The work done is equal to nothing but what? The change in the amount what you are having. 100 minus 0. Or earlier if you have 50 rupees, now you gain something. 250 rupees is there in your hand. When you reach the point B, that is first day you are having 50 rupees. The second day you are having 250 rupees. Okay. How much you have earned in these two, in this day, one day? If they ask you how will you do that, final minus initial, you will have 200. You have earned 200 rupees. The same way, if the initial potential energy UA and the final potential energy is UB, then what is the amount of work done? How will you relate it? This is nothing but the final potential energy minus initial potential energy. So, how will you write that? The electrostatic potential energy. Same, in the expression, you just change it as word. Electrostatic potential energy is nothing but what? Here difference I have to do. Potential energy is difference because 2 points I have taken, right? Between 2 points is equal to what? The amount of work done. So how can you write it properly? If you want to write it properly, then it is nothing but what? The amount of work done in bringing a charge. How much charge you are bringing, ma? You not charge, right? I will write that. So, what I can write? Electrostatic potential energy difference. Here energy only. Between 2 points A and B is nothing but what? It can be defined as the minimum work required to be done by an external force. And without acceleration, I have to tell you. In the earlier I just mentioned, but here when I talk about it, I forgot. Without acceleration, a charge, distance charge, Q0 from A to B. Now what is without acceleration? Here I explain, no? So when two forces, the same thing we are going to. See, what happened? The minimum force applied, external force must be equal to the electrostatic force, and it is opposite in direction, that we know very clearly. When two equal and opposite forces acting on the charge, this is the charge Q0, and one force is acting this way, the external force is acting this way. Two equal and opposite force acting on a body will result in what? The net force will be equal to 0. When the net force is equal to 0, what is the acceleration? Force equal to ma. So acceleration will be 0, not mass. Mass cannot be 0. So acceleration is 0. Acceleration 0 means the charge will move with constant velocity. So you are moving the charge with the constant speed, not with the acceleration. Okay. So this is the explanation. So that's why without acceleration, how much work is done in bringing a charge from one point to the another point, we call it as electric potential difference. So what we can write, the work done in bringing a charge from A to B is nothing but what, ma? UB minus UA. I can write it as simply the change in the potential energy, W. So that's all. So now this is nothing but what? Electrostatic potential energy difference. Then what is electrostatic potential energy? Ma'am, here you have told about difference. So if I want electrostatic potential energy, it is very simple. Now, the same thing if you have understood, consider this. This is the source charge Q and here I have kept one positive charge Q. Definitely it will experience a repulsive force, right? Yeah. And you are doing certain amount of work through external force. Now this is not our concern. Then this repulsive force will be literally 0, ma. Electrostatic force is insignificant. Then at which point? When R reaches infinity. When R is at infinity, what is the electrostatic force? KQ. That is, if you talk about electric field, it is KQ by R square. Our electrostatic force, if we want Q naught by R square. When R tends to infinity, that time what will happen? The force will be tending to 0, right? Because it is the denominator. Anything by infinity will give you 0. The force will be literally 0. So what we can assume, if you consider the point charge is initially at infinity, Q naught, and you are bringing the point that is charge Q naught from infinity to the point A. Now, using the same expression, you write it, W work done in bringing a charge from infinity to the point A. That is nothing but what? Final energy minus initial energy. But there, the force itself is 0. So, there is not any, that is literally by convention what we choose is, excuse me. So, we can choose the electrostatic potential energy. At infinity, usually by convention, what we choose is 0. The reason you can explain in this way, because see, literally there will not be any electrostatic force of repulsion or attraction at infinity. So, no need of doing any work to keep a point charge in that free space. So, that's why the potential energy is considered to be 0. But it is not mandatory to do. You can just choose your origin of reference at any point in time. I don't want to confuse you, but you can. This is the convention that we follow, that it is electrostatic potential energy at infinity is 0. If infinity it is 0, then work done in bringing a charge Q naught from infinity to that point A is nothing but what? The potential energy of Q naught at the point A. Because U infinity is 0, if you substitute, work done is nothing but what? It is simply the potential energy at the point B. So how will you define the potential energy at point A? It is nothing but electrostatic potential energy. It is a point specific. Okay. So how will you define? So electrostatic potential energy at point A can be at any arbitrary point. Okay. It is not mandatory only. This A can be chosen here, here, anywhere you can choose this point A. At any arbitrary point A can be defined as what? Defined as the minimum work required to be done, minimum amount of work done in moving the charge, in moving the charge Q naught from infinity to that point. Is known as what? Electrostatic potential energy, because here the second point is the initial point is at infinity. When you talk about difference, you are having the points which are close. Here the initial point is at infinity. That time the term we are using it as electrostatic potential energy. Okay, is that clear? So without any acceleration, this is the keyword, without any acceleration. So this is electrostatic potential energy. So it is given by the letter what? U. Simply you can say U is nothing but the work done. Okay. The change in internal energy, that is the change in potential energy, is nothing but work done. This already we have seen in 11th standard. Here what it is? U at any point. U at any point is given by what? It is nothing but equal to work done in bringing the charge from infinity to that point. This is the total amount of work done. And what is electrostatic potential? See, now it may, that is, you have to listen carefully. Usually students, in my experience, when they learn it for the first time, they feel like they have understood. But when you start solving numericals and all those things, this confusion, slight confusion comes. But it is quite obvious, you need not worry, just you have to learn it in a proper way, that's all. What is electrostatic potential and what is electrostatic potential energy? So this electrostatic potential energy, what we have seen, it is the minimum work required to be done. Bringing a charge from infinity to the point A, that is nothing but W infinity A is nothing but this much, right? This is in bringing, in moving or in bringing a charge Q naught. So that time we talk about it as what? Work done. Total work done, that is electrostatic potential energy we see. When will you call it as electrostatic potential? This is for Q naught charge. If you do the work, the amount of work done is nothing but what? W infinity to A. That is nothing but the change in the energy. That is nothing but UA. This is for Q naught charge. That time you will use electrostatic potential energy. But what is electrostatic potential when you talk about with respect to unit positive charge? Potential is very, that is what? Very specific term about with unit positive charge. It is not dependent on charge. It is with respect to how much amount of work. This is the total work done in bringing Q naught charge from infinity to that point. If you talk about per unit charge, how much you have done the work, how much work you have done, in that case we call it as electrostatic potential. What is it? See, this is the work done in bringing the charge Q naught, right? Work done in bringing the charge Q naught from infinity. So, in bringing unit positive charge, unitary method ma. In bringing unit positive charge, if you want, from infinity, how much you need to do? That will be nothing but work done per Q naught. Work done upon Q naught. Understood? For Q naught charge, you are doing this much work. For one charge, how much you will do? Work done by Q naught. That's all. This, when you talk about work done in bringing Q naught, that time you will use that as electrostatic potential energy. And when you talk about unit positive charge, with respect to unit positive charge, that time you call it as electrostatic potential. So electrostatic potential, whenever you are learning, you are talking about per unit charge. For bringing one positive charge, how much amount of work you have to do? So that is nothing but potential. If you talk about number of charges, then the total work done in bringing the charge is nothing but UA. It is about, if you take 5 coulomb of charge, then how much amount of work? 10 joule of work if you are doing, then that is nothing but electrostatic potential energy. But the same if you do, what is for 1 coulomb of charge, how much you are doing? Then that is nothing but what? 10 by 5. It is nothing but electrostatic potential. That's all. Per unit charge, electrostatic potential. For the entire charge, it is nothing but electrostatic potential energy. So what is the relation between electrostatic potential and electrostatic potential energy? The VA equal to W by Q naught. What is W? W is nothing but UA. So can I write VA? Simply I will write, it is arbitrary point, right? A. So you need not write A every time. You can choose any point. So electrostatic potential can be defined as what? W by Q. What is W, ma? W is equal to internal, that is energy. So V will be equal to U by Q, or U will be equal to Q into V. So electrostatic potential energy is nothing but what? Is equal to charge into electric potential. And you may ask, see this electrostatic potential, electric potential or electrostatic, anything you can write. Electrostatic potential, whenever you talk about per unit volume, per unit charge, per unit area, that are all constant quantities. So that's why we can simply say that the amount of work done required is nothing but what? The potential energy stored is directly proportional to the charge. How much charge you are bringing, that much amount of work will be required. More number of charges, more amount of work. That means more potential energy will be there at that point. So we can say U is directly proportional to Q also. But this is important, okay? You should understand the difference between potential energy and electric potential. Both are same. When you talk about 1 per kg, like that we are talking now. How much is rice bar? If you ask simply, they won't say per kg 40 rupees, per kg 100 rupees. Even vegetables, everything. Per kg, that is what? Nothing but electrostatic potential. When we talk about, if you want 5 kg, if you want 100 kg, how much you are talking? That is nothing but potential energy. Is it clear? So next we will move to what? Now we have learned new terms, that is U and V. Correct? Since we have. So what is the SI unit? So SI unit is usually from the definition itself, you can say U is nothing but R, work done by charge, it is work done, it is joule, and charge, it is coulomb. But we usually use volts. Okay, the symbol is capital V. So definition of 1 volt is very, very important. What is 1 volt, ma? 1 volt is nothing but from this you write when it will be 1 volt, when 1 joule of work is done moving a charge of 1 coulomb. 1 joule of work is done in moving 1 coulomb of charge. It's nothing but what? 1 volt. Whenever we learned SI unit, immediately we talk about dimensional formula. So what is dimensional formula? Again, what is that? Energy. Energy is nothing but what? Work done. Work done is nothing but what? Force into displacement. That is nothing but energy. What is force formula? MAS. What is mass? Capital M. Acceleration? LT power minus 2. Yes, it is M. So what is the energy dimension formula? ML square T power minus 2. Apply that. ML square T power minus 2 divided by coulomb. Charge is nothing but what? Current into time. For current it is A, time it is T. Now what is that? ML square T power minus 3 A power minus 1 is the dimensional formula of volt. Is it clear? Remember that for positive charge, okay, electrostatic potential is a scalar quantity. That is the next thing, right? I should have told you in the beginning. Electrostatic potential is a scalar quantity. But for positive charge, you will keep the sign as positive. For negative charge, it is the sign will be negative. The sign is very important when you talk about electrostatic potential because it is a scalar quantity. Scalar addition you need to follow, but it is very simple compared to the electric field. There you have to do vector addition. Comparatively, it will be simple, but with the sign convention you need to follow. That is the thing. Now, this is the thing. Why we need to learn this electric potential? So, the thing is, electric field around a charge can be described in two ways. What are others ways? One is through electric field, as we have seen in the first chapter. The second one, we can see it through the electrostatic potential. Both can be used to describe the electric field around a charge. So both are very, very important and they are interrelated. We will soon learn this relation in the next thing. So E and V, they are interrelated. E and V are interrelated and they are used to describe the electric field around a charge. But here the only difference is it is a vector quantity, it is a scalar quantity. Is that clear? So if you have understood, and one more thing, okay, I will do it in the next class. I hope it is clear. Just go through it. Any doubt you can tell me in the next class.